Yeah. Uh, Today to continue the parts that we have finished in Unit 7 last time. I'm wondering if my sound is clear. هل صوتي واضح? I hope that my voice is clear. Okay, so the last times we have spoken about the Unit 7 start the equilibrium. What is the meaning of equilibrium? What's the meaning of dynamic equilibrium? What are reversible reactions? And we also have spoken about the reaction quotient, the Q value, and the K equilibrium value. And how can I use these two with the same equation, but it differs only in when the Q is used and when the K equilibrium is used. So we agreed that the K equilibrium is constant when there is a relationship between products and reactants, when there is equilibrium point. But if you are at any other point and you are not at equilibrium, then it will be known as Q. So today we'll be speaking about the magnitude of the equilibrium constant. So the magnitude of the equilibrium constant. And what does actually the equilibrium constant mean? So we know from the last time that the equilibrium constant is found by the relationship between the products and reactants. So either we can say the Kc is equal to the concentration of the products divided by the concentration of reactants. And every one of these is raised to the power of its coefficients. And if you are talking about gases, this is valid for solutions or gases, any of them. And Kp is valid only for gases. And we will be talking about the pressure of the products divided by the pressure of the reactants. Again, every one of them is raised to the power of its coefficient. The magnitude of the equilibrium constant will tell me how much the reaction has proceeded. So you have just started the reaction. So for example, A and B has given you C. At the beginning of the reaction, you don't have any products yet. At the end of the reaction, because this is a reversible reaction, you will have some of the products and some of the reactants. But to which extent, this will be defined by the equilibrium constant. So I have two main cases. The first case is that the K value is bigger than 1. And the second case, if the K value is smaller than 1. If the K equilibrium constant is found to be more than 1, then I know that there is a favor for the products more than the reactants. So the products are favored. While if it is less than 1, then I will know that the reactants are favored. What does it mean the reactants are favored? It means the reaction did not move. So it almost did not start. I'm still at the reactant side and I did not form any products, or I formed very small amount of products. So the reaction has barely started. So I will say that instead of saying this product favored, I will say the reactants are favored, or this reaction has even started for a very small extent. So the first one means that if the K is very large, I will say the forward reaction moves towards completion. It's almost completely changed to completion. It almost completely, all of the reactants has went into the product side. But if I am talking about the K is less than 1, then I can say that the reverse reaction proceeds to completion. So the reverse reaction, this time instead of the forward, I will say the reverse reaction proceeds or moves towards the completion. So this depends on your K value. If you see the K value, you will know how much the reaction has proceeded and to which extent. So for example, I can compare the K constant of one reaction and the K constant of another reaction at the same temperature. And the one that has bigger K will have more products. So if I have two reactions, let's say reaction number 1, or even the same reaction, but done under different, so A plus B, for example, reaction number 1. And then I have reaction number 2, let's say D gives me E plus F or whatever. This is reaction number 2. The one that has bigger K means that it is going towards products more. So if it has bigger K, this means that it has more products. But this one, it has a smaller K. It means that it did not go to completion. It's actually just trying to go to the product side, but it's failing, especially if the number is very small. So let's have a small example and see how this works as a question. So I have a reaction here between C2H4 that forms C2H2. So the ethene is forming an ethine plus hydrogen. And I have the Kp, the constant Kp, which is equal to 1.4 multiplied by 10 to the power of -7. This is placed in a 1 liter flask at 700 Kelvin and allowed to react according to this equation. Which of the following statement correctly compares the partial pressure of C2H4 and H2 after equilibrium is established? I can see that the value here for P is small, and it's not just small and just less than 1. It is a very small value. So which of the options will be valid? The first option is telling me that the T2H4 pressure is more than H2 pressure, because the smaller the Kp value, the greater the partial pressure of the reactants at equilibrium. Is it reactants really? Yeah, so this looks like a valid answer. I'll say because they are equal, because at equilibrium partial pressure of the products and reactants must be constant and equal. Well, pH2 is bigger than C2H4 because the initial rate of the forward reaction is greater than that of the reverse reaction, while pH2 is bigger than C2H4 because the smaller the Kp, the faster the rate of the reaction. So I can say that at the point of equilibrium, the partial pressure of products and reactants must remain constant. ولكن مش equal. احنا قلنا قبل كده when you start and say about the dynamic equilibrium that the pressures or the concentrations are constant, but they are not equal. So, but which one it will contain more? It will contain more C2H4 than H2. Why did you know that? How did you know that? Because the value is less than 1, and it's not just less than 1. It is very much less than 1, which is very small value. So it tells me that the reaction barely moved, and it almost contains C2H4 and very, very small amount of the C2H2, which is the ethyl. I have another example here. So I have two separate flasks. A solution containing hydroxide ions is combined with a solution containing 1 molar of the appropriate metal. As shown, the ions react by equilibrium to form a complex ion. So this metal aluminum has reacted with the hydroxide to form aluminum hydroxide, and this zinc reacted with hydroxide to form zinc hydroxide. The Kc for the first one is 1.1 multiplied 10 to the power of 33, and this is 4.7 multiplied 10 to the power of multiplied 10 to the power of 17. So which one contain higher concentration of the complex ion? Well, this part actually, which we are discussing now, is very important because many of the questions in the equilibrium doesn't just ask you about a number and wants the number or wants the solution, but it just tries to know if you understand what is the meaning of the K value itself. That's why there is a special part for this section, which we are talking about. It's called the magnitude of the equilibrium constant. So I will tell him, Mr. I can see that 4.6 multiply 10 to the power of 10, multiply 10 to the power of 17, of course, is a smaller value than for the aluminum. So a very large Kc value will tell me that the forward reaction moves towards completion. So I'm expecting this one to have higher concentration of the complex ion. So this one product has formed more than this one because I can see the Kc value is bigger than that in the flask B. So I'll choose A as an answer for sure. Okay, in the next part, we'll try to see how can we manipulate the equilibrium constant and play with it a little bit. This is the next section, manipulating the equilibrium constant. So I have an equation, for example, tells me that 2A, this is one reactant, has reacted with B, another gas, both of them are gases, and it has formed the product C, which is a gas also. So the equilibrium constant concentration Kc is equal to C and A to the power of 2, because its coefficient is 2, and then multiplied by B. Okay, if I want to make a new Kc by reversing the reaction, so I will try to reverse the reaction and write it as C. I will write it here. So I'll just put the products instead of the reactants and the reactants instead of the products without changing anything. And gas and gas. So my new Kc will be reversed. So it will be Kc equal to A squared multiplied by B concentration divided by the concentration of C. So I can say that the new Kc, or let's call it K dash C. I will say it K dash C. This is for the second reaction or the reverse reaction. And Kc is for the original reaction. So I can just say that the K dash C is equal to what? Just the reciprocal of the first one. So it's equal to 1 over the Kc or the original one. So again, in the first equation, number 1, it has Kc products divided by reactants. In the second equation, the K dash C for number 2 is equal to 1 over the Kc. So just by reversing the equation, I can find the Kc just by getting the reciprocal of the original Kc. What if I multiplied the equation by another value? So let's have the same equation. See, let's have the same equation. I will not change it. And again, it will be number 1 here. You can just copy this. I'll get the same equation, 2A plus B give me C, and I will try to multiply everything by a factor. So let's multiply everything by a factor. Let's call it D, so lowercase d, for example, or lowercase c. So I'll just say 2, I'll multiply everything by lowercase c, for example. So I will say 2c, and then I will write this a. So I just multiply this by c, and then I will multiply everything else by the lowercase c. So here again, I will say c, b, and then it will be c, c. They are still all gases. So what will happen to the k, c in this case? So if the original Kc was equal to the concentration of C divided by A to the power of 2 multiplied by B to the power of 1, the new Kc for reaction 2 after multiplying it by just C for everyone is the same C but to the power of the lowercase c. Let's just pick another letter because it's confusing to say C 2 times. Just say D, but just say D. D. I multiplied everything by D here. So if you want to know the Kc without making the equation, or the new Kc for equation 2, I will just say it's equal to the Kc for equation 1, and then I will make it to the power of the factor that I multiplied with, which is d. So if you have an equation and you reverse it, all you have to do is to make the reciprocal of it. And if you have an equation which you multiplied by a certain factor, then the Kc will be equal to the original Kc powered to this factor. So let's have an example about that. So this equation PrCl reacted to form bromine and chlorine based on the information above determines the value Kc for the following reactions at 500. Let me see what is the relationship between this one and the first equation, the second equation, and the third equation. So let's see, for example, the first one, in order to change it into Pr2, I have divided this by 2, or I have reversed it. I have reversed it because I have Cl2 and Pr2 here in the products. I have it here in the reactants, so all I have to do is to reverse the equation. If you have reversed the equation, then the new Kc is equal to what? I will say this Kc, and the new K dash C, or the Kc for this equation number 1 is equal to 1 over 32. So all you have to do is to make 1 or the reciprocal of the original Kc. So that's equal to almost 1 over 32. Zero 0.031. So 0.031. Okay, let's look at the second equation. What happened in the second equation? In the second equation, the same side is here, PrCl and PrCl, but I have clearly multiplied this by 3. So 2 has changed into 6, and Pr2 becomes 3Pr2, and this is Cl2 has become 3Cl2. So in the second one, I have just multiplied everything by 2, by 3. So this means that to find the Kc, or we will call it K double dash C, and this is equal to the same value that you have, which is 32 raised to the power. What's the power? The power is the power of 3. So 32 to the power of 3 will be our answer. So 32 to the power of 3. Which is equal to almost 3.3 multiplied 10 to the power of 5. So 3.3 multiplied 10 to the power of 5. The third one, here PrCl is changed into half Pr2, and this is plus half Cl, and this is PrCl. So it looks like I have done two things. The first thing is that I have reversed the equation. So the 2PrCl has changed into PrCl. Pr2 and Cl2 become in the reactants. That's the first thing I did. And then there is one thing I did more. It was Pr2, now it is half Pr2. So I have divided it by 2. Dividing it by 2 is like saying I have, when I say divided it by 2, it's like saying I have multiplied it by half. So all we have to do is to power it to half. But then we have to make reverse also. So I will say for the third equation, which I will call it K triple C, I have to do two things. The first thing is to make the reciprocal because I reversed the equation. And the second thing is to power it to the factor. What is the factor that I multiplied with? That's equal to half. So I multiplied everything by half. So the PR2, the 2PrCl has changed it into PrCl. So I will raise this to the power of half. So I'll divide 1 by that 1 over 0.031. Let's see on the calculator, it will be 1 over 0.031. need to make 1 over 32 to the power of half. Let me do it. No, that's not good. Okay. This is not the wrong right value. So 32 to the power of half. To the power of half. That's almost equal to 5.65. And then we'll get to the reverse of this one. Almost equal to 0.18. So almost 0.80. So in this one, we have just made the reciprocal of it. This one, we have powered it to 3 because it was multiplied by 3. And this one, we did two things. We reversed it and then we powered by 3. Both of them are done in the same question. One more example here, the C2H4 reacted to form C2 and H2. This is the Kp for it at 1300 Kelvin. And for the second equation also, this is its Kp. Calculate the equilibrium constant Kp at 1300 for the reaction below. So I need to know which reaction I need to use from this. So this is C6H12 forms 3, 2. So I have two combined Kp's here. This one first is reversed to form C2H4, and then this C2H4 is reversed to form C2H2 plus H2. So the only difference in these two equations is that I have 3 moles from this one, but here I have 1 mole. So I'm going to say that if you reverse this one, the C6H12 is going to give you 3C2H4, which is going to give you how many moles from this one? 3 from the C2H2 and 3 from the hydrogens. So now we have 3 moles from the C2H2 and 3 moles of the hydrogens in the product side. So let me see what is the difference between this one and the equation that we have here. Do we have this equation originally? Do we have the Kp? Yes, we have it. It's the same equation here, C2H4. The only difference is that this is multiplied by the factor of 3. And we already studied what we need to do. If you reverse the equation, so if you reverse the equation, we need what to do. And if you make it to the factor of 3, we know what you need to do. So we'll just, but this one, you reverse it here. So it is 13.3. So I will say this one is the one that you need. You need to change from this equation, from the C2H4, into this equation بس. So C2H4 اللي هي موجودة عندي دي, this is equation number 1. I'm gonna change it into C2H4, C2H2 plus H2. So I will say that I will multiply it by I will raise it to the power of 3. So I will raise it to the power of 3. So I will say it's equal to 0.333 raised to the power of 3, because everything is the factor for multiplication is equal to 3. So let me write it down. 0.333 to the power of 3. That's almost equal to 3.69. 3.69 multiplied by 10 to the power of 2. And since I have originally reversed this one, then I need also to reverse this value. So this value was 13.3, 13.3. So this is for the second equation. And then this was reversed, so I'll make it 1 over 13.3. 3, that's equal to 7.59 multiplied by 10 to the power of -2. In order to change this from this to this one, you did two things. The first thing is that you reversed it, and then you have combined the two equations together. So you have reversed it, so you make this new KC1, and then you have also multiplied, by 3. So then you need to make the final KC for the two equations by multiplying both the two values together. So the KP constant will be by multiplication. The first one, which is 3.69 multiplied 10 to the power of 2, multiplied by the second value, which is 7.59 multiplied 10 to the power of -2. So again, I have two equations. I have reversed the first one, so I made the reciprocal of it. I have taken the other one and multiplied by 3, so I make it to the power of 3. Then I needed to combine the two equations. In order to combine the two equations, I have multiplied the two KC for them, that one modified and this one modified, to get the final KC for the whole equation, which is unknown. Okay. The next topic in the equilibrium unit is talking about calculating the equilibrium concentrations. So to calculate the equilibrium concentrations, we said that we are using one of two things. Either he is giving me the values of the concentrations at the equilibrium, already at the equilibrium. In this case, you can just say the Kc is equal to the concentration of products over reactants to their power. Or I'm not giving the concentrations at equilibrium, I'm giving the concentrations at the initial point, And in this case, I cannot use it to find the Kc, because if I am having this, it will not be called Kc, it will be called Q. So it will be called Q instead of Kc. So if I'm giving the concentrations at equilibrium, it is fine. Like in the video, I'm not sure if you saw the video. The Kc, I'm already taking the concentrations at equilibrium, so it is fine to calculate the Kc directly from it. If I am not at the equilibrium and at the initial point, I cannot use it to find the Kc. Otherwise, I will be calculating the Q, not the Kc. And we said that the only way to find it is by using the ICE table. The ICE table is the table that relates the initial concentration of both the reactants with the products by finding the change that happened. The initial change, what happened to it to become equilibrium concentrations, by checking what is the change. Did I add to it or did I remove from it? And usually this is happening because the reaction is not going in one direction. As we remember, if we are having a one direction equation, like if I have HCl that forms H plus and Cl minus, it was very easy to know that if you have 0.1 molar from the HCl, for sure I will be getting 0.1 molar from this one and 0.1 molar from this one, because I'm sure that all the reactants will be converted into products. The issue in the anything which is in equilibrium is that that does not happen. Actually, only part of the CH3COH is going to change into ions, and the rest is not going to do this. And the bigger problem is that I don't know how much. So if I have 0.1 molar from the CH3OH, I don't know how much from this CH3COH is going to be ionized. So actually the value that decreases is an unknown. It is called the -x. And also the value that's going to be formed from the products is unknown. I don't know how much I will get from the CH3OH, COO minus, and how much from the H plus. So also the amount that's going to increase is going to be unknown. The only thing that I am sure of is what? The coefficients. So the stoichiometric coefficients is the only thing that I know will be fixed because I know that the ratios is 1 to 1 to 1. So whatever change happens here is going to happen here in the same ratio. What does this mean? So if I have lost or I have reacted from this 0.1, 0.001, for example, molars or moles, let's say molars, and the amount that's going to be formed here in the products for sure will be in the same ratio. So also will give me 0.001 molar from this one and 0.001 molar. Don't ask me why I've chosen this number because this is just a random number I've picked. It. Just make any number so that it looks like a random number. 36. If you put 0.036 consumed from the reactants, then the amount that's going to be formed in the products is always going to be the same ratio. So also 0.036 and 0.036. The problem is that I don't know how much is going to be reacted. That's why I make this table. So if initially you have certain amount from the reactants, you can find how much was already removed or consumed from it and how much is formed using these tables. So let's just go for exams directly. So I have a sample of something complex called croton nitrile. This is having two forms, a cis form and a trans form, two different compounds. The cis form is allowed to come to equilibrium according to the equation above. So let's say this equation, I will not make it complex like that. So I'll just draw it like that first. This is H and H. This is CH3 and this is CN. No need to know that. But this is double bond CN H, and this is the transform of it. So this one has changed into this one, and the Kc for this reaction was found to be 1.4 at the temperature given 303. What are the concentrations of the cis, which is this one, and the trans of this one after equilibrium is established? So let's go directly and make the table. I know that initially when you started, the sample that you have is equal to 2 molars. The concentration that you have already is equal to 2 molars. And the concentration that I have from this one, the concentration that I have from this one is equal to what? Equal to 0, because he did not mention anything about adding. He did not mention anything about adding initially some of concentration of the trans. So he said I added only from the cis. But how much I have lost from the cis, this is the amount that I don't know, that's equal to minus x. And what is the amount that's unknown also, which is produced in the product, I don't know, but for sure it's the same ratio because the ratio here was 1 to 1. So if I lost 1 x from here, I'm gonna gain 1 x from here. And what is the equilibrium product remaining? You have just to add them together. So we'll say it's equal to 2 molar plus minus, which is minus x. And if you had 0 at the beginning in the products, so 0 plus x, this means that you have x from the products finally. So you can just say that the concentration will be equal to the Kc that you have already given to me. Yeah, for sure he has to give me, because if you don't give me the Kc, how many unknowns I will be having here? There will be a lot of unknowns here, all these unknowns. So he has to give me one value at least. Either he will give me the Kc value or give me one of the products at the equilibrium concentration. So give me one of the concentrations at equilibrium. He has given me the Kc here. It's equal to the concentration of the products. What is the concentration of products? That's equal to X value. So I will just write the concentration that's showing in the equilibrium. And what is the concentration of the reactants? That's 2 minus X. Then the rest, I will leave it to the calculator to find out the X, or we can do it by some math, which is not very difficult. So let's say that the X will be equal to the cross multiplication. That's 1.40 multiplied by 2 minus X. And then I can distribute this saying that X is equal to 1.40 multiplied by 2. So that's 2.80. And then again, 1.40X. And then I will put X plus 1.40. So at the end, I'm going to get X equal to 1.17 mole. So I now have, because he has given me the Kc, I was able to obtain the amount which is lost exactly from the cis form. It is from the 2 molar, I have lost 1.17 molar. Now I have this value. And because we said this is the same value already and the same coefficient, so I know that this is the amount that was gained. So I have lost here 1.17 molar, and I have gained here 1.17 molar. This means that I have ended up with 0.83 just by subtracting 2 minus 1.17, 0.83 molar from the cis, and 1.17, because 1.17 plus 0 is 1.17 molar from the transform. So again, either he is giving me the Kc value here, so it helps me to find the unknown X, or he is going to give me one of the concentrations, like an example that we will see later. For the second example, I have equimolar amounts of I2 and H2. And equimolar means the number of moles of I2 and H2 are equal, and they are all placed in a flask. The gases were allowed to react at 500 Kelvin according to the equation above. What is the partial pressure of HI at equilibrium if the initial pressure inside the flask was 12? So let's put the table. And actually, I like to write it as rise table instead of ice, because at the beginning, we should write always the equation. So we can say I2 reacts with H2 to form 2HI. What is the amount of reactants that he has placed? Did he say anything about putting the amount of reactants? He didn't say anything here. He said that the equal amounts of I2 and H2 are placed, but I didn't put any HI at the beginning. So for sure, there is initially no products. So it is 0 at the beginning. Then he said, I have equal amounts of I2 and H2. So this means that the ratio will be equal. Okay, what did he say about the final pressure of the initial? What is the partial pressure of HI at equilibrium if the initial pressure inside the flask was 12? So the initial pressure of the flask was 12. It says that what is the partial pressure of HI at equilibrium if the initial pressure inside the flask was 12? So inside the flask was already 12. Inside flask equal to 12 atmospheric. If you said that in this flask, if you said that in this flask, the total pressure is 12 atmosphere. Can you find out what is the number of moles of every one of them? You said that they have equal moles, so equal number of moles. So let's say I have I2 pressure and I have pressure of H2. The pressure of every one of them is equal to the number of moles divided by what? The total number of moles. So if you have total number of moles of 2, the number of moles of this one alone is equal to 1. How did you know that? He said it's equimolar. So if you have 2, it is 1. If you have 4, it is 2. If you have 10, it is the half of it. Because they said it's equimolar, means the number of moles of this one and number of moles of this one is equal. So if you have 10 moles, then you have 5 moles of I2 and so on. So it is half the number of moles multiplied by the total pressure. What is the total pressure is equal to 12. Again, the other one is the same. It's equal to half the number of moles. This is the mole fraction multiplied by 12, which is the total pressure. So this means the pressure of every one of them is equal to 6. Again, if you don't remember, in order to find the partial pressure, we used to calculate it by dividing the number of moles divided by the total number of moles, like we said. And that was called what? What was that called? The mole fraction. Multiplied by the total pressure, multiplied by the total pressure. Mister, you said that you have equal number of moles. So if you have 5 here, you have 5 here. So if you have 10 here, you have 10 here. So the number of moles of one of them is always equal to half the total number of moles. So half multiplied by the total pressure, which is 12. So every one of them initially has pressure of 6. Okay? Take care, because some students, whenever they are trying to answer this question, they will go and write down 12 here. They will say, Mister, what is the partial pressure of HI? If the initial pressure inside the flask was 12, so they will say, this means that one was 12. No, it doesn't say HI was 12. He's saying the total pressure was 12. So 12 means the total pressure of everything initially was 12. And initially, there was no pressure of HI, because they said there was no HI made. I just pumped what? I2 and H2 alone. I did not mention anything about putting HI as well. Then, how much this decreased, I don't know, but I know that it has decreased. And this one also, reactant has decreased. So always the reactants decrease, and the products will increase, and it will increase in the same X also, but this time the ratio will be 2, because it's the number of moles is 1 to 1 to 2 here, so it will be 1 to 1 to 2, so 2x. By the addition, to find the last row, I will say 6 minus x, and then 6 minus x, and here 2x. What is our equation to find the Kp? The Kp that you already have here, which is equal to 160, is equal to the pressure of the products, which is 2x, and I need to multiply this 2x by the factor, the power of 2 again. Don't forget, it's 2x, and then there is again a factor of 2 in the power. So 2, because the number of moles was 2. So again, this is 2x, because that one is 2x, and there is a 2 here, because there is a 2 here, divided by 6 minus x multiplied by 6 minus x, which is actually 6 minus x squared. Again, I can go to the calculator, or I can find manually that x is equal to 5.18. So I know what is the change that happened. I know that I2 has lost 5.18 atmosphere, and it started, the pressure of I2 started with 6 and lost 5.18. So at the equilibrium, it becomes 6 minus 5.8. Minus 5.8. Minus 5.8 does not require a calculator instead, it's just 0.2. And the pressure of H2 at equilibrium is equal to, again, 6 minus 5.18. So that's equal to 0.2 atm, of course. And the last one is 2x. So the pressure of HI is equal to 2 multiplied 5.18. So that's equal to what? That's equal to 10.2. Yeah, that's equal to 10.4 atm. Again, this was the same idea like the previous one, but that one was concentration and this one was pressure. And in the exams, usually he is linking these two much together. In the AP exams, usually linking the idea of the partial pressures together with the idea of the equilibrium. So this is a basic idea that always happens in the exam. Find the partial pressures using this equation. The partial pressure is equal to the mole fraction, number of moles multiplied by total pressure. And then from it, you can find the equilibrium, either finding the equilibrium constant or Kp, or find the unknown concentrations like we did here, or unknown pressure. Okay, this is the last part of the topic is the representation of equilibrium by drawing. So we have taken the representation of particles, but that was not in equilibrium, that just was normal reactions. When we have drawn the particles, if you remember, when we have drawn the particles and changed these particles into different look in the products, for example, so we'll do the same here, but we will do it for the equilibrium. Well, I have an example for the famous example N2O4 that forms NO2, or let me have the example directly. We have the example directly. So A2 here has reacted with 2P to form A2P2. The gases A2 and B are placed in empty 1 liter rigid vessel at constant temperature. The particle diagram represents the content of the vessel after equilibrium is established. So this drawing is shown at the point where the equilibrium is already done. So I have A2 and 2P. Based on this information, what is the equilibrium constant Kc for the reaction above at 25? So if you want to find the Kc, you need to find the concentration of the products and you need to find the concentration of the reactants. We said that every particle here, so every particle is representing 1 mole. So every one of these small spheres, either black or white, is having a representation for 1 mole. And the total volume is also 1 liter. So whatever number of moles you will find is equal to directly the concentration. So I can say that the first reactant, which is A2, let's see, A2 concentration is what? And the 2P concentration is what? Concentration is what? And the A2P2 concentration. I can see that A2P2 is 1 piece, then 2, and then 3, and then 4. So 4 times, so this means that it is 4 moles in the liter, so it is equal to 4 molar. So the concentration is equal to 4 molars. And the A2, which is the white one, is found 2 times only. So this is found 2 times. So that's equivalent to 2 molars. And the P is found 1, 2, 3, 4 times. So that's equal to 4 molars also. So let's write down the Kc. The Kc is equal to the product concentration, which is A2P2, divided by the reactants, which is A2, multiplied by the other reactant, which is P, and the P will be power to 2. So the concentration we found here is already equal to 4 molar, and A2 is equal to 2 molar, and this one is equal to 4 molar, but this one is raised to the power of 2. So I have 4 divided by 2 multiplied by 16, or 4 divided 32, that's equal to 0.125. We just found the Kc by just finding the number of particles from the diagram instead of being given as a direct numbers. One more is there. So this 2x gives me y at 25 degrees at equilibrium constant. For the reaction above, which of the following particle diagrams best represents the system at equilibrium? Assume that each particle in the diagram represents a concentration of 0.1. So the x is the white one. So I can say the concentration of x is equal to 1, 2, 3, 4. And you said that's equal to 0.1 only, not 1 like the last time. So it is 0.4 molar. And the other one is y. That's also 4 particles. So it is also 0.4 molar. So which of the following particle diagram presents the system at equilibrium? Is saying that when you are at equilibrium, what is your QC for every one of them? Because I have the value already of the KC. And if you want to be at equilibrium, what is your Q? So if you find the division of the y divided by x to the power of 2, and at any point that's equal to Q. And if you find it at equilibrium, that's equal to K. So if your Q is equal to K, you are at equilibrium. So what we are trying to find is which value of this will be equal to the K, which is 15. If it is less than, if the Q is less than K, or Q is more than K, you are not at equilibrium. You are favoring here the forward reaction more, and here you are favoring the backward reaction more. So let's see, that's equal to 4 over 4 squared, that's equal to, احنا قلنا مش 4، قلنا 0.4 over 0.4 squared. So that's, and this one is equal to 2.5. And then this one, 1, 2, 3, 4 over 3. الوايت احنا قلنا عليها الوايت هي الاكس، يبقى احنا عايزين نعمل الواي الاول، والواي هي البلاك 3، يبقى دي 0.3 over the 5 times, so it is 0.5 squared. So 0.3 over 0.25, that's equal to 1.2. It's not the answer also. The third one is equal to 0.6 because 6 times, and this is 0.2 squared because 2 times. So that's equal to 15. That's our answer. That's our answer. And just for confirmation, we'll do the last one. That's equal to, again, y, which is the black, which is 5 over 3, 0.5 over 0.3 squared, that's equal to 5.6. So the only answer in which the Q is equal to 15, and this means that the Q is equal to K, so this means that this is the one which is at equilibrium. And that's what he asked it for. Okay. We'll have a short break and then we'll come back to review the Louchatelet principle fast. Thank you. Okay, let's see some questions first. Miriam, let's start. This is based on the information above. Which of the following expressions corresponds to K equilibrium for the reaction represented below? So I have two equations here. I hope the screen is clear. This one is, I can make it a little bit bigger, like that, so it's clear. I have K equilibrium K1 and K2 for the first equation and for the second equation. And I need to find it for the equation, this equation. Okay, which one will represent this equation, Miriam? Let's try to do it. We need to play with the two equations. So let's try to play with the two equations, okay? And this is the equation that I need to form. So I'll put it here in the top. This is the one that I need to reach to. So this is FeO plus H2, and this is Fe and H2O. I need to play with these two equations. So let's see the first equation, H2O plus CO gave me H2 and CO2. How this relates to the equation? I have to flip this equation. When I flip this equation, I will have H2 here at the beginning at the reactants, and I will have H2O as the products. Okay. So I will reverse the equation. It will become H2. So it will become H2 plus CO2 give me H2O plus CO. So when I do like that, what will be the K that I need to find, the K equilibrium that I will get? If I flip the equation, what do I do to the K?
Make it negative.
Negative or positive if it is endothermic and exothermic reaction. But for K equilibrium, we said if we reverse the equation, it will be the reciprocal of it. Huh? It will be the reverse. It will be the reciprocal. So I will say K equilibrium equal to 1 over the first equation. What's the first equation, K equilibrium? That's K1. So I will say it is 1 over K1. Okay, let's see the second equation. Yazid, let's see. I have FeO and CO and Fe and CO2. Do I need to make any changes, Yazid? Well, it is okay.
It's okay.
It's okay. No need to make any changes. So I will say that the K equilibrium for the final equation will be equal to K2 directly. I don't need to make any modifications. Okay, let's try to put the two equations together. So I'll try to put all the two equations together. What is the two equations? هنضيف الأولانية مع الثانية ونشوف إيه اللي حصل. أنت عملت يا مستر the first equation. What did you do to it? You make it H2. خلاص احنا كتبناها H2 plus CO2. This is the first equation after manipulation. H2 plus CO2 give me H2O and CO. Okay. And the second one, you said you will write it as it is علشان هي no reactants هنا مع reactants already مع reactants هنا. So no need to change number 2 in anything. FeO plus CO and Fe plus CO2. لو أنا حاولت أكتب الاثنين equations مع بعض and I see what cancels out. ازاي اكتب الاثنين equations مع بعض يا زيد؟ I will write all the reactants together and all the products together and try to cancel it out. So what are the reactants? I'll write all the reactants together and then I will write all the products together and see what cancels out عشان اتاكد انها هتديني الايكويشن بتاعتي. So H2 plus CO2, this is reactants and this is the reactants also. CO مظبوط كده؟ This is are all my reactants. حطيتهم مع بعض by the green. And then I will put all my products together اللي هي H2O plus CO H2O plus CO plus Fe plus CO2. Let me cancel out يا زيد ها. Which ones is repeated هنا and هنا؟
CO on CO2.
CO and CO2 are both repeated. ممتاز. So let me look. It's exactly my equation here. FeO plus H2 give me Fe plus H2. So what I did is correct. اللي أنا عملته ده مظبوط بالظبط كده. I will just have to reverse the first one and keep the second one as it is. طب يا مستر أنت قلت لي how do we get فاكرين إحنا عملنا إيه المرة اللي فاتت in order to get the final we multiplied the two by each other. فكرك what did we do يا يزيد فاكر؟ I multiplied the first k by the second k. عملت لهم multiplication. هنا I will do the same thing. So what is the first k? That's equal to 1 over k. And what is the second k? That's equal to k2. ليه يا مستر الأولانية عملت لها reciprocal لأن أنا عملت لها reverse؟ ليه الثانية أنا عملت لها سبتها زي ما هي؟ أوكي. So the k equilibrium is equal to 1 over k multiplied by the second one which is k2 and that's equal to our which option this is equal to K2 يعني equal to K2 على K1 على K1 K2 over K1 this is our right option. Okay, so whenever you manipulate any equations these are the rules. If you reverse it equation what happens to the K you will find the reciprocal of the K. So we will make 1 over the K. If you did not do anything, it will not be changed. If you multiply it by factor, then you will put k to the power of this factor. If you multiply it by 2, you will put k to the power of 2. If you multiply it by half, k to the power of half. Let's see one more. Julian, you can type if you wish in the chat. Let me see what is the question first. So I2 give us 2i. The dissociation of I2 is represented by the equation. This is the value. For the information, which of the following can be concluded about the reaction? The reactant is favored, the product is favored, the concentrations are equal, the reaction reaches equilibrium relatively slowly. What did we know from this value? It's equal to 9.1 multiplied 10 to the power of -4. Is it big value? Is it small value? What did it tell us exactly? What do you think, Julia? Is it a small value? It's a big value? If it is small or big, ولا بتقول لي ان هما الاثنين concentrations are equal at equilibrium? What do you think? You can type in the chat if you wish also. Yeah, very good. ممتاز. It is a small value, yeah, mister. And since it is less than 1, I don't need to know how small it is, but I know that it is less than 1. And since it is less than 1, then I can just say that the reactant is favored over the products. It did not move to the products. The reactants are mainly there. So if I open the container, I will see mainly I2 much, much, much more than the I concentration. Okay. So I have another one here, the copper and bromide. This is my K1. The copper bromide plus bromide give me this K2. I need again to find my new equation, which will be called K3. So let's try to see how can we find K3. Miriam, what do you think I should do for the first equation? Should I leave it as it is? So that I just reverse it. I just multiply it by a factor.
Same equation.
So first equation, what do I do to it?
Nothing.
I can't hear you, the sound is very low.
Nothing.
Nothing, very good. And the second one?
Times -1.
Times -1. Let me see. This is this is copper, and this is copper. This is CuPr. Okay. What about the second one, Mr.? This is CuPr plus Pr minus CuPr. I can see that two of the reactants are still there, the same in the second equation also, Miriam, you see? I can see that the copper and Pr in the first one is the same as here. And in the second equation also, I can see that it's not changed. What do you think? PR minus and CuPr2 minus. I have here also PR minus and CuPr2 minus. So I think that they are both the same, non-changed for both of them. So I can just say that this means that the K equilibrium is equal to K1 and that K equilibrium is equal, we'll say it's K3, so we'll say it is K3 is equal to K1 and K3 is equal to K2. So all I have to find K3 is just multiply them two together, just combine them together. So, Mr. I don't see that this is correct. Okay, let's prove it. So just multiply them together. Let's prove it. I will put all the reactants again together. So these are my reactants, and I will put all my products as background. So again, I'll put the reactants all together. This is Cu plus and Br minus, and this is Cu, Br, and Br minus, right? This is all our reactants. This is reactants and this is reactants. I'll put them all together. And then the products together also, I'll put CuPr and CuPr2 minus. So I will put CuPr and CuPr2 minus. Can you cancel out, Miriam? Can you see if you can cancel it out? Oh, why did you make these colors like that, Mr.? Make it a different color. Can you see what can be canceled out? The CuPr2 minus. Which ones can we cancel out? Can you see?
CuPr.
CuPr and CuPr, and then nothing else, خلاص? Nothing else. So let's add these two together. I will put Cu plus, نشوف الحاجات الباقية. What's remaining? زائد 2Pr minus, and this is CuPr2 minus. Is this our final equation? This is our final equation. This is what we need. So this means I did not do anything in our equations, ممتاز. I just kept the equations as it is. I did not manipulate anything in them. I just kept them as it is. So just add them together, which means that I will multiply. So don't forget to multiply. If you adding the equations, what you will do, Yazid, for the k's, to multiply the k value for them. Adding the equation, multiply their constant values. Okay, for them. Okay, so this means that I need just to multiply the two numbers, 2 multiplied 10 to the power of 8, multiplied by 4, multiplied 10 to the power of -3. So I have 2 and 4 and 10 to the power of 8. That's equal to 8 multiplied 10 to the power of 5. Okay. In this one, I'll be trying to calculate the equilibrium concentration. So let's see. I have here at 350 Kelvin, 1 mole of sample of X and 1 mole sample of Y are pumped into a previously evacuated 5-liter rigid container and allowed to reach the equilibrium represented. Which of the following is true at equilibrium? هل الZ أكبر من X؟ هل Y أكبر من Q؟ هل الZ equal to Q أكبر من Y؟ How can we find this? Can we find it by numbers or can we find it how? Yazid, can we try this one? Let's see it together out. You will help me. So I have here an equation which tells me that x plus y give me z plus q. So I have 1 mole of sample of x and 1 mole of sample of y. So the number of moles or the concentrations of both of them is equal. Is this correct or no? Yes, Mr. Concentration is equal to what, Yazid? Equal to number of moles over volume. And the volume is the same, right? And the number of moles is the same. So I can say that x is equal to y, right? I can say that the concentration of x equal to y, both of them is equal to 1 over 5. Now, what about Z and Q? Bumped into a previously evacuated 5 liters. What about Z and Q? What is the number of moles? I don't know what is the amount decreased from here, and I don't know what is the amount decreased from here, but let me tell you something, Yazid. If you lost one from here and one from here, how much do you get in the Z and Q? So how much do you get in the Z and Q? Isn't it the same value؟ مش نفس الفاليو بالظبط؟ كده let me ask you again. احنا قلنا if you have x plus y give you z plus q and you lost، مش هقول x بقى عشان هي already x. I will say minus a and this is minus a. What will be the value here, Yazid? It will be plus
A.
plus a. ممتاز. So if you lost 1 mole from here and 1 mole from here, how much you will make here? Also 1 mole from here, because the ratio is 1 to 1. So minus 1 mole and minus 1 mole. I don't know what is the value, but let me see that it is equimolar value. So 1 1 this will be. طب if you form it 10 يا مستر and 10 this it will. انا مش عارف ان دي بتساوي دي فعلا ولا لا. لا مش شرط يا مستر، مش شرط دي بتساوي دي. يعني ممكن تكون ده ما نقصش 1، ممكن نقص اقل شويه، يعني ممكن نقص 0.05، ممكن نقص ده مثلا 0.05، ما نقصش ال1 كله. لكن اللي انا متاكد منه ان الزد والكيو ايكوال. I'm sure that Z and Q both of them are equal. طب بس بص لي كده يا يزيد على الفاليو زي ما قالت لنا جوليان في المثال بتاعها بالظبط، على الفاليو بتاعت الكيسي. ايه رايك في الكيسي؟
It is small, so reactants are
ايوه
favored.
جميل. small solid reactants are much more. يعني ايه في دول ينفع ان الزد تكون اكبر من الاكس
No.
كونسنتريشن بتاعها؟ طب ينفع ان الواي تكون اكبر من الكيو؟ تنفع الواي تكون اكبر من الكيو. طب ينفع الزد بتساوي الكيو اكبر من الواي؟ لا
No.
برضه ما تنفعش. خلاص يبقى very good. يبقى احنا بناء على الانفورميشن دي، since this one is very small value, so I'm expecting the concentrations of Z and Q to be minimal concentrations compared to the concentrations of the reactants X and Y. طيب what about the last one? I'm again saying that the number of moles of X is equal to Y and Z is equal to Q. ده الكلام ده أنا عارفه، لكن is X equal to Y equal to Z and Q? If you said like that, then this is totally incorrect. كأنك أنت بتقول the concentrations equal in the equilibrium. We did not say at all it is equal. We said that it is just constant concentration. Let's see next one. Okay, so a student places 0.400 molar sample of liquid methanol into evacuated rigid container and heats the container. At this temperature, methanol is completely vaporized and begins to decompose. When equilibrium is reached, 60.5% of the original number of moles have decomposed. Calculate the value of the equilibrium constant for the reaction. I don't know any numbers, Mr. Lewin. Let's write the equation and hope for the best. This is CH3OH give us CO plus 2H2. So give us CO plus 2H2. You started with 4 moles of this one. And luckily it is 1 liter. So we can say directly it is 4 molar. I don't know what is the amount that I have ended with. No, I know, because he said at the end how much is decomposed? 60.5% of the original have decomposed. So what is the percentage remaining? So 60.5% decomposed. So what is going to be at the equilibrium is 100 minus 60.5%. مظبوط كده؟ صح كده يا جوليان؟ So 100 minus 60.5. 100 لو أنا بدأت ب 100 وخلصت 60.5. So this means that I have 39.5 molar here at the end. At the end, when I reach the equilibrium stage. So I will say that's equal to 39.5. استنى انت بتألف. Why did you make this 4? مش حد يقول يا جماعة. Why did you make this 4? It's not 4. It is 0.4. I'm sorry. 0.4. So if you started with 0.4, how much did you end with? 39.5% remaining out of the 0.4, so that's equal to 39.5 over 100. Oh, multiplied by 0.4, so you ended with 0.158. Tani, if you are wondering how did we get this one, again, this is the 100% of the 0.4 moles. Out of it, only 60.5 is decomposed, and this is the amount which is remaining, which is 39.5% from the 0.5 moles. That's equal to 0.158. What is the change? Can I find the change here, Julian? How do I find the change? Because the change here is very important. This is what's going to tell me how much is increased or decreased. So if I have minus x here, this will be what ratio plus x, and this is plus 2x. I don't have KC here. I need the KC. So I have to find one of the unknowns. He gave me the x. What is the x, Julian? Can you try to find it and tell us? Minus x. What is the x? You told me, Mr., that the equilibrium is equal to the addition of these two.
0.558.
ممتاز. So 0.4 minus 0.158 equal. لا. Can you try again? Can you try again? Try again. So what do I need, Mr.? أنا كان عندي I used to have 0.4 and now I have 0.158. So how much I lost? Just subtract, right? Can we subtract? Yes, because if you started initially with 10 and you ended with 4, so this means that what is your x value? Your x value,
0.242.
bravo, like 0.242. So it is 0.2 x equal to 0.242, and x is very valuable here because this is the amount that will be increased here. Did he say I put anything at the beginning? No. Here 0, 0. So I have added, if I lost 0.242, so I gained also 0.242 here, plus 0, that's 0.242. What about Yazid, the H2? How do I find it? I just have to add x again, but this time multiplied by what, Yazid? By 2. So it will, yes. So it will be how much? X equal to
0.48.
Jamil. Can I now try to find the KC? How do I find the KC finally?
Multiply.
Yeah, so tell me the equation for the KC. This KC is equal to what?
0.158 multiplied by 0.242.
Okay, is it the products over the reactants or the reactants over the products?
Products of reactants.
Okay, so I need the carbon monoxide, which is 0.242. صح كده؟
242.
Okay, and what is the H2?
0.484.
Don't forget to the power of
2.
ممتاز عشان coefficient 2 divided by
0.4.
احنا بنعمل initial concentrations ولا الفاينل concentrations؟ ايه رايك عشان
0.158.
برافو عليك 0.158. Okay, then what is the final value? It will be equal to
0.358.
جميل 0.35 almost 0.358 or 0.359. ممتاز. That's it. Okay, this is some of the questions. We'll be getting more questions on the website. كانت جوليان عندك مشكلة. Did you try again, Julian?